Now in the last example, we were left with a formula for something that we might not really know how to graph. So if we're finding solution curves, it's cool to be able to kind of think, what would that solution actually look like? Now, to work out what solutions might look like, you might want to use the chain rule to actually find the second derivative in an example like this. So if we have the first derivative, then we really just need to differentiate that to find the second derivative. But here's the catch. We have a formula for y dash. This is dy dx. It's differentiating y with respect to x, and it's got y in it. There aren't any x's there to pay respect to, and that's why we need to use the chain rule. So if we're taking a first derivative like this, obviously we've found the solutions. We found last time that we had y equals 0, y equals 1, and y equals some other more complicated stuff. And here I've got d being any real number. So we can use that first derivative to look at what various solution curves, either above 1, between 0 and 1, or below 0, if there are any in those three particular places, what they might look like. Now remember that our solution curves generally don't cross each other. So the fact that we've got two horizontal ones means that if we're looking for solution curves, we've got three kind of places to look. But just analysing the gradient is enough. The gradient is something, the concavity gives you more of a story. So let's start by just thinking about what the gradient would be. If y is greater than 1, then we've got here a positive number, and if it's greater than 1, this is multiplied by a negative number. So any solution curves, if they existed up here, would have a negative gradient. If y is less than 0, then we've got negative here, and we've got 1 minus a negative number, that's a positive. A positive times a negative, they'd be negative gradients down here as well. But if y is in between 0 and 1, then it's going to be positive, so this number would be positive, and 1 minus something between 0 and 1 would also be positive. So the gradients of our solution curves in here are positive. So we've got some sort of slopes that are all going this way, okay, and we can think that through. But what's the concavity doing? Well, let's differentiate this with respect to x. Now, to differentiate some y's with respect to x, we need to use the chain rule to differentiate the entire global picture of this thing, which means that we get 1 minus 2y, just as our global picture. But then we need to multiply that by dy dx, because we're not differentiating with respect to y. We're differentiating with respect to x when we find this second derivative. So we need to multiply all of that by y dash. Now we can come up with another version of this. If y dash is something that we already know, we could say, hey, the second derivative is equal to 1 minus 2y multiplied by y dash, which is all of this stuff. So we end up with this. Or we could even say, instead of using this version of y dash, we could use this version, which is factorised, and get this thing factorised even further. We would have y, 1 minus 2y, 1 minus y. Now, the value of this form is that it's really easy to spot where there might be points of inflection. You get points of inflection when the second derivative is equal to 0, and those are going to happen at 0, a half, and 1. Now, these are going to happen at values of y equals 0, y equals a half, and y equals 1, not x. So instead of looking this way to find our points of inflection, as we often do, we're actually looking at the y parameter here and thinking about where they might occur. Now, we don't have a specific solution curve here. This is just a general solution. So we're imagining all sorts of solutions that could occur here. But now we've got the ability to analyse not only the gradient in various sections of the graph, but also the concavity there. And if we know that we've got our changes in concavity at 0, half, and 1, we've already got 0 and 1 here, we can mark in a half. Then we can consider whether the curve is concave up or down in this zone or this zone, because it will continue to have that concavity above that and below that. So looking at what happens in between, say, 0 and a half, if y is in between those, let's pick something like, say, a quarter. We've got a quarter, that's positive, minus, 1 minus 2 quarters, that's a half, so that's positive. A positive multiplied by a positive, multiplied by a positive, we'll find that we've got positive concavity there, which means that the curve is concave up when it's in this zone here. So something that's swooping up this way, we've already seen that the gradient is positive, and we also know it's concave up, so it's moving this way. Whereas in between half and 1, and here I'm not using this to be a coordinate point, I'm thinking here as a range of values for y. Between half and 1, let's pick something like 3 quarters. 3 quarters is positive. 1 minus 2 lots of 3 quarters, well, that's negative. and 1 minus 3/4, that's positive. So we've got a positive times a negative times a positive. The concavity would be negative there, which means that it's concave down. So possible curves could be concave up and then concave down in this section. So now we've got an idea for things that are maybe doing something like this as they move through this zone and approaching but not crossing those solution curves.